तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have been considering methods of proof. We found that if the form of the theorem is in the form of a tautology, then by its nature it will be a theorem. Then we considered statements of the form P implies Q. So, for that we considered that if the statement of the theorem is of the form P implies Q, several types of proofs are considered. One is vacuous proof, where if you show that P is false, because the implication will be true when the premise is false, if you show P is false, then P implies Q will be true. That sort of a proof is called a vacuous proof. Then you have what is called a trivial proof. The implication is true if Q is true. So, if you just prove Q is true, then because it is an implication, P implies Q will be true. Such a proof is called a trivial proof. Then you can assume that P is true and prove that Q is true. That is called direct proof. We saw an example of a direct proof. The last one is indirect proof or proof of the contrapositive. This also you can call as proof of the contrapositive. We know that the contrapositive of P implies Q is not Q implies not P. So, instead of assuming P and then trying to prove Q, you can assume not Q and try to prove not P. Such a proof is called an indirect proof. We shall see an example of indirect proof now. Consider this statement: a perfect number is not a prime. Now, what is a perfect number? A perfect number is one where if you sum up the divisors, it should be equal to the number. For example, 6 is a perfect number. The divisors of it are 1, 2 and 3, and if you sum them up, you will get 6. 1 plus 2 plus 3 is 6. 28 is a perfect number because the divisors are including 1, 1 plus 2 plus 4 plus 7 plus 14. 1, 2, 4, 7, 14 are divisors of 28 except itself, and if you sum them up, it equal to 28. So, the theorem states that a perfect number is not a prime. Now, the contrapositive statement, actually this theorem you can look at it like this: if x is a perfect number, it is not a prime. The contrapositive statement will be, if x is a prime, it is not a perfect number. So, we can easily prove this statement. What is a prime? If x is a prime, then it has got only divisors 1 and x. The divisors of x are 1 and x divisors, and leaving out x, you have only 1. So, the sum cannot equal to x. So, it is not a perfect number. So, this is the sort of a proof you give, and such a proof is called an indirect proof. Later on we will see one more example at a different stage. Now, instead of having one statement P implies Q, you may have something like that: P1 and P2 and P3 and Pn implies Q. The statement of the theorem can be something like this. In that case, how would you prove it? Now, this you can write as not of the contrapositive will be not Q implies not of P1 and P2 and Pn, or not Q or not of not Q or not of P1 and P2 and Pn. This will be Q or, using De Morgan's law, this will be not of P1 or not of P2 or not of Pn. And because R is associative, you can write it as Q, and you can also use several Q's, Q or Q or Q, like that you can use, or not of P1 or not of P2, etc., or not of Pn. Now, each Q you can combine with one P and write as Q or not of P1 or Q or not of P2 or etc., or Q or not of Pn, and this will be not Q implies not P1. This will can be written like this, because the R you can convert again into implication. It will be like this, or not of Q implies not of P2 or and so on. So, it is just enough if you prove not of Q implies not of P of I for some I, where I is between 1 and n. So, if the statement is of the form P1 and P2 and P3 and Pn implies Q, then it is enough if you just prove one statement like this. Again, some sort of an indirect proof we are using. Now, the statement can be something like this: P1 or P2 or P3 or Pn implies Q. This you can write as not of P1 or P2 or P3 or Pn or Q, and using De Morgan's law, this will be not of P1 and not of P2 and not of P3 and not of Pn or Q. Using distributivity, this will be not of P1 or Q and not of P2 or Q, etc., and not of Pn or Q. So, this you can write as P1 implies Q and P2 implies Q and Pn implies Q. So, you must prove for every Pi that Pi implies Q. P1 implies Q, you have to prove P2 implies Q, you have to prove P3 implies Q, and so on. You have to prove each and every of these statements. This is called proof by cases. So, if the statement of the theorem is of the form P1 and P2 and P3 and Pn implies Q, using the contrapositive, it is enough if you just prove that not of Q implies not of Pi for some I. It is enough if you prove just for one I, then the result will hold. Whereas, if the statement of the theorem is of the form P1 or P2 or P3 or Pn implies Q, then you have to prove P1 implies Q, P2 implies Q, Pn implies Q, every one statement you have to prove. So, let us consider an example of proof by cases. Let this denote the min operation. Min operator, that is A this B gives the minimum of A and B, minimum of A and B. Let us restrict ourselves to the set of integers. So, we consider the set of integers. Then we want to show that this operator is associative. That is, we want to prove that A for all A comma B comma C belonging to I. For all A, B, C belonging to I, the operator min is associative. Now, how do you prove? You can use proof by cases here. If you take three integers A, B and C, what are the possibilities? The possibilities are that A can be less than or equal to B, less than or equal to C, or you can have A less than or equal to C, less than or equal to B, or you can have B less than or equal to A, less than or equal to C, or you can have B less than or equal to C, less than or equal to A, or you can have C less than or equal to A, less than or equal to B, or C less than or equal to B, less than or equal to A. These are the 6 possibilities. There are no other possibilities. Now, for each one of this, if you prove that the associative property holds, then you are proving the result. This is called proof by cases. There are 6 cases, and for each one of the case, you prove that the result is true. Let us take A less than or equal to B less than or equal to C. Then what will you get if you take A minimum B union C? This will be A minimum, then minimum of B and C, that is because B is less than or equal to C, you will get B, and the minimum of this will be A. On the other hand, if you take the right hand side, A min B min C will be, you have to take the minimum of A and B, that is A, then you have to take the minimum of A and C, that is also A. So, you prove that the left hand side is equal to the right hand side, right. So, the associative property holds. Like that you have to prove for each and every case. Let us take one more case, take the 6th case. So, let us consider the case when C is less than or equal to B, less than or equal to A. In that case, the left hand side is A min B min C which is equal to what is min of B and C, that is C, and what is min of A and C, that is C. And the right hand side you have A min B min C. What is the minimum of A and B, that is B. Then what is the minimum of B and C, that is C. So, left hand side is equal to the right hand side. So, we have to prove for each one of the 6 cases, and this sort of a proof is called proof by cases. Then we come to the important type of proof which you would have learned in school also, that is called proof by contradiction. Proof by contradiction. Or reductio ad absurdum. We have already seen what is a tautology, what is a contradiction, and what is a contingency. A contradiction is a propositional form which is always false, something like P and not P. This will always be false. Okay. So, in this type of proof, supposing you want to prove some statement P, you want to prove some statement P, then you assume that P is not true. Then from this, by some argument, you arrive at a contradiction, something like that Q and not Q. You arrive at a contradiction Q and not Q, that is assuming P is not true or assuming not P, you arrive at a statement of the form Q and not Q. That means your assumption is not correct, that is not P is not true, that is P is true. This sort of a argument is called proof by contradiction. Let us take an example. Root 2 is not a rational number. We want to prove that root 2 is not a rational number. This is statement P. So, you assume not P. What is not P? Not P is root 2 is a rational number. Now, from this you show that not P implies another statement Q, where Q denotes root 2 is P by Q, where P and Q are integers and also relatively prime. Relatively prime. What do you mean by relatively prime? P and Q do not have common factor. So, you assume that root 2 is equal to P by Q, where P and Q do not have any common factor. So, if root 2 is a rational number, obviously it can be written in the form of an integer by an integer, and so you get this statement, not P implies Q. So, what do you get? You get root 2 is equal to P by Q. Now, squaring you will get 2 is equal to P by P squared by Q squared, or P squared equal to Q squared, 2Q squared. So, p squared is even, p squared is even, which would mean p is even, right. So, p is even means p you can write as 2r. So, what do you get? 2r the whole squared is equal to 2q squared, or 4r squared equal to 2q squared, or q squared equal to 2r squared, which would mean q is even. Q squared is even, so q is even. So, q is of the form 2 of s. So, p is of the form 2 of r and q is of the form 2 of s, where r and s belong to a set of integers. That means, p and q have a common factor 2 and not relatively prime. Okay. So, from this actually starting with q, q is root 2 can be expressed in the form p by q, where p and q are integers and relatively prime. From this you come to the conclusion that not q, that is you do not express root 2 as p and q where they do not have a common factor. They have a common factor. You come to the conclusion that if you assume like that, you will come to the conclusion that they have a common factor and not relatively prime. So, from this and this, using hypothetical syllogism, you will get not p implies not q. Okay. From not p implies q and q implies not q, you will get not p implies not q. So, you have both not p implies q and you also have not p implies not q, and you started with not p. So, using mod exponents to this you will get not q, and using mod exponents to this you will get q, and by addition you get not q and q, and this is a contradiction. This is a contradiction. Usually you denote it like this. Contradiction, you use this symbol to show that you have arrived at a contradiction. So, assuming not p, you have arrived at a contradiction. So, the assumption is wrong or false, not p is false, so p is true. This is the way, therefore, p is true. This is the way you prove proof by contradiction. This is a method which is very commonly used. Proof by contradiction is a very famous or very widely used method for proving results. We shall take one more example. Let us consider one more example. This is a well known problem known as the halting problem. You know that if you do not have any restriction on the memory or of the computer or for the time which a program can run, if you allow these two conditions, then given a program ultimately will it halt or not. This is known as the halting problem. That is, if you have a computer program, can you say whether it will halt or whether it will not halt? We are not putting any restriction on the memory size, we are not putting any restriction on the time for which the program can run. So, under that circumstances, you can you show whether it will halt or not, or can you design an algorithm which will tell you whether it will halt or not. Now, whether a program will halt or not will depend upon the input it gets. Okay. So, for some input it may get into a loop, or some input it may halt. So, testing whether a program will halt or not will depend on the input. So, for simplicity we shall consider only input free programs. We will consider programs which are input free. So, we are even restricting the problem a little bit. We are considering only input free programs and asking the question whether the program will halt or get into a loop. Can you write a program halt? That is, in essence it is like this. Can you write a program or a procedure halt for which the input is a computer program P, and this will tell you yes, P will halt, or it will tell you yes, no, P will not halt. So, it can give you two answers, yes, P will halt, or no, P will not halt. The question is, can you write such a program, such a procedure halt? The thing is, you cannot write such a program halt. That is what we want to prove. You cannot write a procedure halt like this, like that. This is the theorem you want to prove. Now, how we do again? We will use proof by contradiction. Assume it is possible to write a procedure halt. Assume it is possible to write a procedure halt. Then you have to show that you are arriving at a contradiction. In that case, you can write a program contradict as follows. You can write a procedure contradict like this. Begin. If halt of contradict equal to yes, then begin while true print x end else stop, then an end for this begin. You can write a procedure contradict in this manner. It says if halt of contradict is yes, then begin while true print x else stop. Now, you can note that contradict is an input free program. There is no input for that, it is a straight away a straight program. Now, will contradict halt or not? The question is, will contradict halt or not? Will this procedure contradict halt? Look at this. If it halts, there are two possibilities. It halts or it does not halt. Let us see what happens here. Supposing it halts, then in this run this program, halt of contradict should give you an yes answer because contradict halts, and in that case what happens? This portion of the program will get executed, that is you keep on printing x like that, it will never end. So, keep on printing x, that is it does not halt. On the other hand, if contradict does not halt, halt of contradict is not yes, it is no. So, the else portion should be executed. So, it will stop. If it stops means it will halt. So, if it does not halt, you come to the conclusion that it halts. So, the argument goes like this. If it is possible to write a procedure halt, then it is possible to write a procedure contradict like this. And what happens to contradict? If it halts, it does not halt. If it does not halt, it halts. This is something like a paradox. It is a paradox, or it is a contradiction. So, assuming that it is possible to write a program like halt, then you come to the contradiction, and so the assumption that it is possible to write a program like halt is not correct. It is not possible to write a program like halt, or halt does not exist. A procedure like halt does not exist. This is the famous halting problem, but instead of programs, Turing defined it for Turing machines, and even in 1936 he was able to see what is possible by a computer and what is not possible by a computer. And this halting problem, or this is called undecidability. Undecidability. This undecidability of the halting problem is a major breakthrough in mathematics and theoretical computer science. Once it is people came to know about this, many other problems for which they did not have algorithms, they realized that they are undecidable problems. An undecidable problem cannot have an algorithm. You cannot write an algorithm for an undecidable problem. It is a very strong statement. It is not that you do not know how to write the program, or somebody else does not know how to write the program, how to solve the algorithm, or how to solve the problem, or how to give an algorithm for the problem. It is just that you cannot have an algorithm for such undecidable problems. Okay. So, let us continue with other types of proofs. Now, we have considered implications. We also have statements of the form P is equivalent to Q. P if and only if Q, or P is a necessary and sufficient condition for Q. We will come across several statements of theorems which are of this form. Generally, it is proved in this manner. You prove it in two parts, P implies Q and Q implies P. You prove it in two parts like this. On rare occasions, you also have another method of proving this. That is, you start with some x is equivalent to y, some well known statement x is equivalent to y, and from this maybe you write an equivalent statement here, and an equivalent statement for y here, then another equivalent statement x2 here, another equivalent statement y2 here, and like that. Finally, after a few steps, say n steps, you get something like this, xn is equivalent to yn, where this will represent p and this will represent q. This is a rarely used method, but it is also used in some cases. But the general way you prove an equivalent statement like this, p is equivalent to q or p if and only if q, is by proving p implies q and q implies p. Or if you want to prove that p and is a necessary and sufficient condition for q, first you prove p is a sufficient condition and then you prove it is a necessary condition, or the other way around. So far we have considered statements which did not use any quantifiers. Next we shall consider the theorems, how to prove theorems which have quantifiers in their statements. When we use quantifiers, the statement can be of this form: not there exists x p of x, or there exists x p of x, not for all of x p of x, or for all of x p of x. The statement of the theorem can be in any one of the 4 forms. Let us consider one by one. Now, if you consider the statement to be of the form not there exists x p of x, usually for such theorems the proof is given by contradiction, proof by contradiction. So, you assume there exists x p of x and show that you arrive at a contradiction. Now, if you consider statements of the form there exists x p of x, such proofs are called existence proofs. Existence proofs. You show the existence of something. So, they are very famous. Existence proofs are famous in several branches of mathematics like differential equations and so on. Here there are 2 types of proofs: constructive and non-constructive. A constructive proof gives you the element x. It tells you what is the element x or some element c for which p of c is true. Sometimes it gives you the exact element c, or sometimes it gives you an algorithm to find that element c, how to find that element c. Such proofs are called constructive proofs. In a non-constructive proof, no clue is given as to which c will satisfy that p of x, or which c will give you the value p of c, but by some other argument starting from something else you prove and so on. Such proofs are called non-constructive proofs. And usually there are some cases where you will not get the exact element c, but some range in which you will get the element c. That is, it will tell you that you can get c between some values a and p, though it may not exactly give you the value c. Such proofs are very common. You would have known about Rolle's theorem and mean value theorem. Rolle's theorem, mean value theorem. I will not state the theorems, but give a graphical expression. Rolle's theorem states that if you have a function f of x and at point A and B, that is if f of A equal to f of B equal to 0 and the function is continuous and differentiable, then at some point you will get the tangent parallel to the x axis, or at some point you will get a maxima or a minima point. This value C is not really given, but it is between A and B, that sort of a range is given. Similarly, mean value theorem is graphically like this. If you have a point A and a point B and the function is continuous and differentiable in this range, then this is the function. At some point C between A and B, the tangent will be parallel to the line, this line, function value. I am just giving you the graphical interpretation of Rolle's theorem and mean value theorem. So, these are examples of existence proofs where you make use of the statement of the form there exists x p of x. And if you have statements like not for all of p of x, you know that not for all of x p of x can be written in the form there exists x not of p of x. So, if you bring the not inside, for all will become there exists. So, this is equivalent to saying like this. And again now the statement is of the form there exists x p of x. So, both constructive and non-constructive proofs can be given. Now, if you have the statement of the theorem as for all of x p of x, usually what you take is take an arbitrary element C of the universe and prove P of C. Then by universal generalization you get for all of x P of x. Take an example. Consider for all of x is even is equivalent to saying x cubed is even. Now, how do you prove that? Take arbitrary C and show that in two parts. This is equivalence. So, you have to show it in two parts. C is even implies C cubed is even. This is one part. How will you prove that? See, you use direct proof. C is equal to 2k. If C is even, you can write C is equal to 2k. So, C cubed will be 8k cubed, where k is an integer. So, C cubed is even. The other way around, you have to prove C cubed is even implies C is even. Now, you use indirect proof here. That is, instead of showing this, you show that C is not even implies C cubed is not even. That is, C is equal to say 2k plus 1, it is odd like this. So, C cubed will be 2k plus 1 whole cubed will be 8k cubed plus 12k squared plus 6k plus 1. So, you can see that this is even, this is even, this is even. So, c cubed is odd with that 1. So, c cubed is not even. So, you have proved that c cubed is not even. Now, use universal generalization. You get, because c is arbitrary, you get for all of x, x is even is equivalent to saying x cubed is even. This is the way we prove using quantifiers. So, we consider some methods of proofs. There are some other methods like proof by induction, and induction itself you have two types of induction, weak induction and strong induction. That we shall learn after we learn sets and how to define a set inductively. Some more methods are also there, but these are the main methods of proofs and we have considered them. Now, when you have a formal system, we ask two things about a formal system, that it be powerful enough to prove all valid assertions, that is all those assertions which are true regardless of the universe of discourse or the interpretation of the predicate symbols. We ask two questions. One is this: is it powerful enough to prove all valid assertions, all those assertions which are true regardless of the universe of discourse and the interpretation for the predicate symbols. The second question is this: is the system powerful enough to prove all assertions which are true of some particular universe with a specified interpretation of certain predicate symbols. As an example, you can consider natural numbers with predicates corresponding to equality and identities of arithmetic. We have to say that logicians and mathematicians have been successful with regard to the first question or the first type of problem, which is called usually you say where is a predicate or a well formed formula of predicate calculus valid or not. In the case of propositional logic, it can be decided. In the case of predicate first order logic, it is partially decidable and you can give an algorithm. Whereas mathematicians have not been very successful in dealing with problems of type 2. And Gdel showed that this not being successful is rather inherent in the system itself. That is, you cannot be successful in dealing with problems of such type. What he proved is you cannot have a complete and consistent system for integer arithmetic. You cannot have a complete and consistent system for integer arithmetic. This is called Gdel's incompleteness theorem. A consistent system is one in which you cannot prove both P and not P. If you in a system you prove both P and not P, the system is inconsistent. A complete system is one in which every true statement you can prove. What do you mean by proving? Starting from axioms, using rules, every true statement can be derived. Such a system is called a complete system. What Gdel proved is, if a system is consistent, it cannot be complete for integer arithmetic. For that he used what is known as a Gdel numbering. Each sentence can be given a number, that number is a very large number, and he used something like this, x is a number, it is a Gdel number, he used what is called a Gdel number. The statement of the theorem is like this: the statement whose Gdel number x is not a theorem. I am roughly writing this. The statement of the theorem was something like this. It said that the statement whose Gdel number is x is not a theorem. What happens if you are able to, starting from axiom, if you are able to derive this particular statement, then it is false. Saying that it is, you cannot prove that is false. If you are able to prove, starting from axioms, this theorem, this statement, then it says that you cannot prove it, it is not a theorem. You cannot prove it starting from the axiom, then it becomes false. So, you arrive at a contradiction. Now, suppose you are not able to prove this starting from the axiom, if you are not able to prove this statement, then it is a true statement about the system which you cannot prove. So, the system is incomplete. It is a true statement, but you will not be able to prove that statement. So, it is incomplete, the system is incomplete. This is the essence of Gdel's incompleteness theorem. Of course, I am not going into the details of the way in which the numbers, Gdel number is chosen and how the statement of the theorem is, that particular statement is written and so on. So, mathematicians have been successful in dealing with problems of type 1, and they have not been successful of problems of this type, and this is rather because of the inherent difficulty, or this lack of success is inherent in the system itself. Okay. So, we have considered some methods of proofs which you already have studied in schools and so on, and this is just to tell you how the formal method can be used to prove theorems, and how you look at the formal way of proving theorems when the statements of the theorems are in particular forms.